I will try to explain the Thevenin's theorem. I'm using this circuit for that, and it can be seen in the circuit. It's a DC circuit, so the sources are DC, the voltage source, the current source, and it's only resistances there. But we have to understand that the theorem is equally applicable for AC circuit when the resistances will be replaced by impedance, so inductive or capacitive reactance as well as resistance, and also the sources can be AC, so once we replace them with RMS value, it's equally valid. So here the theorem states like any part of the circuit can be replaced by an equivalent voltage source and a series resistance. So the whole part, let's say we want to replace the circuit here, this port, let's call it A and here B. So we want to replace the entire this side of the network using Thevenin's theorem. So that means the whole of this part can be replaced by a single voltage source and a resistance, a series resistance, and this voltage source is called Thevenin's voltage source, and this is Thevenin's resistance. And once it is the whole thing is replaced, we can rejoin this part here AB, and we will get the same current here. If the current for the original network is say I5, here we will have the same I5. So what the benefit of using Thevenin's theorem is, once we are interested in the response of in a particular branch, whether it's a voltage response or a current response, just a particular branch of a big circuit we are interested, so we are not interested in any other branch, so we can replace the other external branches, so or the remaining part of the circuit we can replace by Thevenin's theorem. So let's say we are just interested in the current of this branch I5, so we are not interested in any other currents or voltages, so we can replace the whole remaining part by Thevenin's theorem. Now the question comes how to replace. The thing is the Thevenin's voltage, how to find the Thevenin's voltage and how to find the Thevenin's resistance. So to find the Thevenin's voltage, what is done, the circuit is disconnected at this point where we want to find the response, so basically this part is taken away, so this is made open, and once it's opened, so the remaining part of the circuit stays the same, only this part is opened, and then the open circuit voltage here is calculated, VOC, that's the open circuit voltage that's calculated here, and that open circuit voltage is, and all the sources remain like that, inside sources, and everything else in the circuit remains the same. So this open circuit voltage is the Thevenin's voltage. Once we find it, we can use any other network analysis method to find the open circuit voltage, and then like for this one we have multiple sources, so we can use probably principle of superposition, and we can find the voltage here for each of the voltage source, each of the sources, voltage source and current source, and then we can add up to find the open circuit voltage. That will be the particular technique to solve this particular circuit, but I'm just saying that's how we can find the Thevenin's voltage. And when it comes to the Thevenin's resistance, what happens is again the same thing. This is made open, this whole thing. We'll just erase this part here. So basically this is still open, and what is done now is the Thevenin's equivalent resistance looking here is calculated. So equivalent resistance, but before calculating that equivalent resistance we have to make all the sources inactive, all the sources in the network inactive. That means when we say inactive, we have to, the voltage sources, we have to make them short circuit, and the current sources whatever we have to make them open circuit. So basically that's the way to make the whole of this network inactive. So what will happen, I can redraw this circuit once it's made inactive. So this is there, this is there, and this R2 will be there, and this current source will be open now, so we will have like open there, and then the resistance R, this one is R3 and then R4, so R3 is there, R4 will be there, so we just need to find now, and this is our A and B, so R4 there, R1, R2, so we just need to find the equivalent resistance here. And when for this particular circuit, so the current source is inactive by making open circuit, because in order to make it inactive we have to make the current through it zero, and that's only possible if it's open circuit. Similarly, the voltage source, the property of a voltage source is it maintains a fixed voltage, but if we make it short circuit it can, so that's the way to make the voltage source inactive. So that's here inactive. So for this particular arrangement, we can see that since there is a break here in the circuit, the equivalent resistance will be just R4. But this is just because it's very simple for this particular arrangement. But whatever the circuit is, we just need to find the R equivalent, and that R equivalent is actually R Thevenin for this one. So once we do those particular thing, find this particular voltage source and value of voltage source and resistance, we uh, we actually have the Thevenin equivalent circuit, this one. And once we have the Thevenin equivalent circuit, we can just rejoin our desired branch, and we can calculate the voltage and current through it. It's a very simple, it turns into a very simple series circuit, and then it is solvable. And there is also once we are not interested in any other branch for this particular circuit, since we are not interested in any other branch, it actually becomes very simple by using Thevenin's theorem. So yeah, maybe I will do an example later. I actually had a video on Thevenin's theorem even earlier, but I thought that the audio quality of that was not very good, so I thought of making this video again, though it's a bit different circuit, but I just wanted to talk about the principle, the theorem itself. So yeah, thank you.